So we have now seen examples of the curl for two-dimensional vector fields. But what happens in 3 dimensions? So in 3 dimensions, your vector field produces a different vector field which will have both x, y, and z components. And as I said, it's quite ugly trying to plot 3-dimensional vector fields. So I'm not going to do it. Instead, I'm going to do like an artistic representation of how this would look like. For example, imagine you start with your vector field f, which are the red arrows here, going like in this circle. And now I plot the vector field curl of f, which are the blue arrows here. So obviously, you just have to apply kind of the rules of the right-hand rule and the rule of putting a windmill at a location and seeing in which direction will this windmill rotate. But this direction, now you have to take into account the axis of rotation, and the axis of rotation will tell you the direction of the curl of f. Okay? So basically, you have to use your right-hand rule to know which direction the thumb will point. Of course, this is a very simplistic case. Let's look at a more complex scenario. So here I have a vector field f, which looks very complicated, right? We have like a circulating field, but at the same time, this circulating field is rotating in some way. So if you calculate the curl of f, you will see these blue arrows here doing this shape like this, okay? So calculating the curl can really lead to very beautiful patterns. And it's nice to think that these beautiful patterns are actually patterns that happen in nature because, for example, the equation, one of Maxwell's equations of electromagnetism for magnetostatic fields is that the curl of B is equal to a constant times the current density vector field J. Okay? So imagine that we have a current, which is the blue arrow. Okay? So those blue arrows are a current. So we have a wire that we put into a coil like that. So this is our wire carrying a current. So now the current is equal to the curl of B, which means that the magnetic field would be the red arrows, because the curl of these red arrows give you the blue arrows, which will be the current. Okay? So indeed, if you create a current and you put it in this shape, the magnetic field that these currents create will have these shapes shown here. It will be like magnetic field lines going around of the current at every point. Okay? And as you know, you can actually visualize magnetic field lines using the famous experiment of magnets with iron filings. And you see this beautiful vector fields whose curl is equal to the currents that are inside of the magnets. Okay? So visualizing the curl in 3 dimensions in theory would be extremely nice, but in practice, when I try to do it in Mathematica, it's always very confusing and ugly. So we have to just believe that they would be beautiful if we could plot them, right? Okay. So that was the curl in 3 dimensions. See you in the next video.